Hello, I'm Brian Young, and today we're doing Module 26203, Electric Lighting. Let's get started. 26203, Electric Lighting. Successful completion of this module prepares you to do the following: explain the relationship between the human vision and light, explain how the human eye operates, identify characteristics of light, and then you'll have some performance tasks that your instructor wants you to do. Install one or more of the following illuminators: surface mounted, recessed, suspended, or track mounted. Electric lighting is used extensively in residential and commercial buildings, industrial plants, and outdoor sites. Lighting systems and fixtures ideally provide illumination that fits the setting while maximizing comfort, minimizing eye strain and fatigue. This module introduces the principle of human vision and characteristics of light. It also introduces a variety of light sources and describes the operating characteristics and installation requirements of various lighting fixtures. Perception of light. Electric lighting is used to supplement or replace sunshine in places where we live, work, and play. The color, the luminance, which is the brightness, it's a measure of the intensity of light traveling in a given direction from any surface. It's measured in candela per square meter. The term is commonly used to express brightness. And contrast between lit surfaces can provide the following positive results: improve ambiance, provide illumination for various tasks, improve the efficiency of workers, aid in selling merchandise, increase productivity, reduce mistakes, increase safety, and focus attention. Regardless of the application, well-designed electric lighting serves to provide illumination for the performance of visual tasks with maximum comfort and minimum eye strain and fatigue. Yeah, you don't want some bright glaring lights in your eyes. That causes a lot of eye strain. Human vision is the process that occurs partly in the eye and partly in the brain. Light enters the eye through a thin transparent layer known as the cornea and passes through the pupil, the opening in the iris. The light then enters the lens, which focuses the image until it finally reaches the retina. So it focuses on the optic nerve or the rods and the cones. We have cones that are color sensitive, and we have rods that are black and white. You have many more rods than you do cones. The rods are used at night for night vision. This is the human eye can distinguish well over 1 million different colors and tints or shades of colors. At any instant, the eye can see objects whose brightness varies by nearly 10,000 to 1. With changes in the opening of pupil and chemical changes in the retinal cell, the total range of brightness the eye can see exceeds 1 million. Rod and cones send their information through the optic nerve to the brain. In the brain, the image is remembered and compared with other images and memories to influence emotion, action, and thought. Therefore, lighting plays an important role in how people feel about their surroundings and buildings that they occupy. This is about 8% of males, and a much smaller percentage of females are lacking in one or more types of cone cells or have variations in a cone cell that shifts the peak color sensitivity. This condition makes it difficult to distinguish between certain colors and in some cases to see color at all. Characteristics of light. 1.2.0. Visible light is a form of radiant energy in a very small portion of the electromagnetic spectrum. Radio waves and X-rays are also part of the same spectrum. Because of how important light is to life, this section will discuss some of the characteristics of light. So here's a very narrow bandwidth of visible light. And if you look, it's Roy G. Biv, right? Red, orange, yellow, green, blue, and then violet or purple. And if you're lower than red, you're infrared. And if you're higher, it's a higher frequency, basically. It's a shorter wave. A higher frequency than violet, then it's ultraviolet. If it's a longer or lower frequency, Then red, it's infrared. Incident and reflected light. Incident light is that uh, light that hits the surface or object regardless of the source. If an object's not self-illuminating, any light that comes from it is called reflected light. So any light that comes from a surface that's not self-illuminating. If you have a white piece of paper on a desk, the white light coming off that paper is reflected. The incident light comes from the lighting fixture above you hitting that white piece of paper. Light that hits a surface or an object. It includes light from self-luminous objects such as the sun or electric light, as well as reflected light. Some surfaces and materials reflect light better than others. Light colored or highly polished surfaces reflect more light than darker colored or dull surfaces. This is because white light and colored materials absorb less light energy than dark or dull surfaces do. The way things get their color is they absorb all of the spectrum of light, except for the light that they don't absorb, it gets reflected out. So when you see something that's red, like my shirt, it's absorbing all of the other colors in the spectrum. It's not absorbing the red. The red is being reflected off of my shirt. So you could say my shirt is every color but red, because the red is being reflected. So this is the percentage of light reflected. White plaster, 90 to 92%. Mirrored glass, 80 to 90%. White paint, 75 to 85%. Polished aluminum, copper, highly polished, stainless steel, limestone, marble. Look at dark red brick. Dark red brick is 10 to 15%. That's a very low amount of light being reflected off of that. If you have something that's black, it's absorbing most all of the colors in the spectrum. It's not reflecting any of them. Absorption, reflection, and refraction of light. This is a highlight. It says all the light striking an object's surface will be absorbed, reflected, or transmitted through, which is refracted, as shown in figure 3. The relative portions of absorption and reflection are transmitted, and transmission are determined by the object's composition, surface texture, overall shape, and internal complexities, as well as the wavelengths of the incident light. It's real interesting. They had some tinted glass on a job I was on. There were panes of glass they were going to install, but before they were installed, they were just stacked up on the walls. They had about 10 sheets of this darkly tinted glass. It was to keep some of the sun out, but not all of it. You wanted to be able to see through the window, but you also wanted to block some of the sunshine coming into the building. Walking past it, when your angle of incident was very shallow, meaning you were very close to it and looking almost straight on, it was like a mirror. You could see things in the room. You could see reflected light coming from that piece of glass very clearly. But as you walked past it, when you got to a certain angle of incident, all of a sudden the reflection on the surface disappeared, and you no longer saw the reflected light from the room. You saw through the glass. You saw the layers of glass behind that glass. You saw the wall. Now you were refracting the light through that big stack of glass. So there was an angle of incident at which you went from reflected light to refracted light. It was at the time, it was very interesting to me. So this is what we used to call refracted. They're calling it transmission. I don't know why. Reflected is bouncing off. Absorption means it got absorbed into the object. Usually solid looking objects absorb light, and then refracted or transmitted as being pushed through the object that is translucent or clear. When light energy is absorbed by an object, it's stored in the form of heat. This explains why walls, floors, metal, etc. feel warm or hot when exposed to direct sunlight or light from a strong artificial light source. When light energy is reflected from an object's surface, different wavelengths of light will have different amounts of reflection depending on the chemicals at the surface. This is how an object's color is created. When light energy enters a transparent surface at an angle, it's bent at different angles according to its wavelength. Red bends the least, while violet bends the most. This is called refraction, the bending of a light wave or ray as it passes through medium of different density or layers of different density in the same medium. and it has many uses in science and other professions. So here are the colors. Sometimes the book is going to tell us something and we're going to take it as gospel and we're not going to question it. They're going to ask you, how many colors does refracted light have? When you put it through a prism and you split the white light into its rainbow, how many different colors are there? The answer is 6. Red, orange, yellow, green, blue, violet. There are 6 colors. That's it. I'm not going to tell you I agree with it or disagree with it. I don't want to confuse the issue. The answer is 6. And thus, 6 is the answer that we will write. All right. When all the wavelengths of light of the spectrum are presented to the eye in nearly equal portions, white light is seen. When a narrow beam of sunlight passes through a prism, as shown in Figure 5, the light spectrum is refracted at different angles according to its wavelength. Both Figure 4 and Figure 5 show the 6 common names for colors. Since the spectrum is continuous, the actual number of colors is infinite, but tests show that about 125 individual colors can be identified within the visible spectrum. All right. Again, it used to be a question on the test. I don't know that it still is a question, but if they say, how many colors does refracted light have? Your answer is 6. And this is partly why our sky is blue, because of refraction, the sunlight coming through our atmosphere. And at night, when the sun is at a steeper angle, we see red. So that's your beautiful sunsets, your oranges and your reds. They're the last colors of light that are visible before the sun disappears over the horizon and then everything goes dark. Okay. As previously described, the amount of light energy absorbed by an object depends on the wavelength of the incident light striking the object. All objects absorb light different wavelengths in different proportions. This is called the selective absorption. Spectral analysis of the spectrum of light coming off of an object. Scientists use that all the time to figure out what elements are in a star or a comet or a nearby planet. Practically all colored objects owe their colors to selective absorption in some part of the visible light spectrum, with resulting reflection and transmission in the other selected parts of the spectrum. This characteristic gives us our color distinction when viewing different objects, surfaces, etc. So something that's red, something that's green, something that's yellow or orange, they're reflecting different wavelengths of light. Understanding these basic concepts of light and how it's perceived will help you select the appropriate electric lamp or luminaire to provide light in any residential, commercial, or industrial application. We're going to use the term luminaire for light fixture. I guess it was about, I don't know, 16 years ago, the International Code Book or the National Code Book, the NFPA 70, they changed the word fixture to luminaire because in Europe that's what they know them as. A complete lighting unit consisting of a light source such as a lamp and the parts designed to position and protect the light source and distribute the light. It may also include components to modify the power source to meet the needs of the light source. So that's a luminaire, it's a light fixture. Cone cells are sensitive to different colors, and colored objects owe their color to selective absorption. All right. Sources of light. Evaluate light sources and luminaires to solve common lighting needs. Compare light sources and trends in their use. Choose auxiliary equipment needed for different light sources. So it says from prehistory to the present, various sources have been used to create light. Each has required energy, first from fuel such as wood or gas, and now from electricity. Safety, ease of use, and cost have been the criteria for selecting the light sources we use today. Because nearly every source of light uses electricity, an electrician must understand the differences between the light sources, the advantages and disadvantages of each type, and the requirements for their installation and use. If you have a really nice bright light and it puts out a lot of lumens, but the lamps are very expensive and they go out every 3 months, that's probably not a good choice for a customer. They don't want to have to be replacing the lamps or having an electrician come and replace them. Some of the lamps, like halogen or sodium vapor, you can't touch them with your fingers. You've got to wear little white cotton gloves, or they come in a little foam wrap, and you take them out of the box and you make sure you never touch it with your fingers. If you get any oil on the light of the lamp from your fingers, when they heat up, they will blow. They heat to a high temperature, and the oil causes the lamp to heat unevenly. And when that happens, the glass will shatter. I've seen it happen. So the light will be no good. You have to be very careful when you're replacing a lamp. You have to know what kind of a lamp it is and know not to touch it. Regular incandescent lamps, yeah, you grab them with your bare hand, screw them in, they're fine. They don't get that hot. They don't get that hot that quickly. Lumen maintenance decreases over time due to physical and chemical changes in the source. Manufacturers of fluorescent lights and bulbs, lamps, they'll tell you to replace those lamps when they become 85% efficient. We don't know what 85% efficient is, so I always used to tell my customers to change them once a year. Every January, just take all of the fluorescent lamps out and replace them with new lamps, and your ballast will last for 30 years. You don't, your ballast will last about 3 years. It's a lot more expensive to replace a ballast than it is to replace the lamp. The lamp's about $2 or $3. The ballast is about 30. When comparing two lamps in the same type, the lamp with greater light output will have a higher efficacy. Efficacy is the visible light output of a light source divided by the total power input to that source. It's expressed in lumens per watt. The theoretical maximum of efficacy is 683 lumens per watt at 540 nanometers, resulting in a green colored light. That's stuff you don't have to know. For non-incandescent sources, auxiliary components are required, such as a starter, an igniter, a ballast that changes the input voltage, an electrical component, and fluorescent and high-intensity discharge luminaires that provides the required voltage surge at startup and then controls the subsequent flow of current through the lamp during operation. I don't want to lie to you, but it's my understanding. I think that fluorescent lamps start at about 600 volts and then they run at about 250 volts. That ballast will give you that input surge to get the fluorescent lamps lit, and then it'll lower that voltage. Doesn't mean they can't run on 120 volts. You have ballasts that run on 120 volts, but the output is higher to excite the electrons inside of that tube. The coloring, this is a highlight, the color rendering index is defined as how well a light source matches the solar spectrum. So sunshine is about 100 on the color rendering index. So something that's 95 to 100 on the color rendering index is said to be very close to daylight. Color rendering index is a measurement of the way a light source reproduces color, ranging from 0 to 100. The higher the index number, the closer the colors are to how the object appears in full sunlight or incandescent light. So doctors' offices, they want something that's 95 or better on the color rendering index. They will have to look for people, see if they're pale or jaundice, or if they're reddish, if they have a fever. They look at the color of your skin, and they need a good color rendering index in order to be able to do that. Color rendering index differences among lamps are not usually visible unless the difference is greater than 3 to 5 points. Note that the color rendering index of different lamps can be compared only to the source having approximately the same color temperature. Color temperature expressed in kelvins is commonly how lamp manufacturers describe the color tone, warm or cold. It's counterintuitive. They talk about kelvins. They're talking about heat on the Kelvin scale. They have something called an imaginary black box, and they take that black box, or black, I forget what they call it, black, basically it's a rectangular solid, and again, it's imaginary. Somebody came up with this, and they start heating it, and as they start to heat it, it goes from black to a dark brick red, and then it turns orange and yellow and white, and then it goes blue-white, and then it goes like or green-white, and then blue-white. So they have this scale from 0 to 10,000 degrees. And they imagine that at 3,000 kelvins and lower, those are described as warm tones because they're reddish or orange. Even though 5,000 or 8,000 kelvins is higher on the temperature scale, those colors tend to be blue and we call them cool colors. So it's counterintuitive. You just have to kind of wrap your brain around it. A color temperature of 3,500 Kelvin is considered moderate in tones, producing a balance between warmth and coolness. Color temperatures of 4,100 Kelvin and higher are considered cool in tone, slightly biased toward blues and greens. At 3,000 is biased towards yellows and reds. Okay. Unlike Celsius and Fahrenheit, Kelvin is not expressed in degrees, therefore no degree symbol is used. Standard incandescent lamps. Incandescent lamps were first invented over 200 years ago and became practical for use by 1880. Since then, they've remained much the same, with the only significant refinement being a change from a carbon filament to a tungsten filament around 1920. Their basic construction has not changed, although the number of sizes, uses, and other details have increased tremendously. So this screw base is called an Edison base. Thomas Edison came up with that screw base, and this is a pin, a button, and then it's insulated from the shell. The shell is metal, and that's the neutral or the return, and the button is the hot or the ungrounded. So whenever you wire a shell of a light, code says that the hot or ungrounded conductor must be wired to the button at the bottom of the shell. It's safer than wiring 120 volts or higher to the shell of the screw shell. Okay. But basically, you take a bulb or a bubble of glass and you pull the environmental air out of it. You take all the oxygen out of that and you fill it with some inert gas. It keeps the filament from oxidizing. So the filament will heat to the point of incandescing. It'll be bright. It'll show off visible light, but it won't burn up. It won't oxidize. If you try to make a light with a tungsten filament, that filament will only last about 10 to 15 seconds. Then it'll burn up in the oxygenated air. It'll oxidize and it'll burn. Remove the oxygen and it won't oxidize. So it continues to burn. Some of them are good for 1,000 hours. Okay. In an incandescent lamp, light is generated by passing electrical current through a filament, the resistance of which causes it to heat to the point of incandescence. The self-emission of visible radiant energy from an object heated above 750 Kelvin it typically occurs when an electric current is passed through the filament of an incandescent lamp. So, if the voltage to the lamp is increased by 5%, for example, the filament gets about 2% hotter. The light output increases by about 20%. However, the lifespan is cut in half. So you increase the voltage by 5%, you decrease the lifespan of that lamp by 20%, by a fifth. That's pretty wild. All right. Let's see here. What are they trying to tell us? Relationship of rated lamp voltage to lumens, watts, and lamp life. So here's the lamp life, and here's the lumens per watt. When you have a low lumens per watt, you have a longer lifespan. And as these two cross, there's a sweet spot where you get output of about 100 lumens for 100 watts. And the lifespan, I don't know. I don't know how they've got this number. They have no numbers on the lifespan. I don't know if they're going to say that's 100% of whatever the rating is of the lamp. Maybe that's what they're saying. But as you increase the lumens, you increase the watts, you also increase the brightness of the light. You're actually reducing the lamp life. The advantages of incandescent lamps include they're available in many sizes, shapes, and wattages. No ballast is required. They're dimmable. They offer a very high color rendering index approaching 100. The The disadvantage of incandescent lamps includes the following. They're the least efficient light source with an efficacy of 5 to 22 lumens per watt. Over 90% of the energy they consume is given off as heat, as seen in Figure 8. The heat can damage the luminaire and its wiring, as well as increase air conditioning costs. There are some recessed fixtures that go up in your attic, and they will say, IC, insulation contact. The insulation can touch that recessed fixture. Others will say non-IC, non-insulation contact, meaning you have to dig the insulation 3 inches away from the light. If the insulation falls against the light, the can that the lamp is in, that light will overheat. When you have a customer and they say, yeah, my light will go off like every 2 minutes. It'll be on for a while, and then it goes out. And then it comes on all by itself, and then it goes out. Well, that's because it's got a thermal protector internally of that light. And when it gets too hot, the thermal protector will open and disconnect the power. And when it cools off to the point that the thermal protector closes, then the light will come back on for another couple of minutes, and then it'll keep going out. So they'll say there's something wrong. Check. It might say maximum 60-watt lamps, and they might have a 100-watt lamp in that fixture. Regular people, non-electricians, they don't read that little label that says maximum 60 watt. If they can screw a 100-watt light bulb in it, they're going to screw a 100-watt light bulb in it. And then they're going to get that blinking effect because the light's getting too hot. Here's a highlight. It says the resistance of the filament is much lower when it's cold than when it's lit. Okay. They have the shortest life expectancy of all types of lamps, typically between 750 and 2,000 hours. Over time, the tungsten evaporates from the hot filament, deposits on the envelope, darkening it and reducing the light output. The envelope being the glass bulb, that glass holder. Tungsten. Tungsten halogen incandescent lamps, referred to simply as halogen lamps, are a refinement over the standard incandescent lamp. Two changes allow halogen lamps to have a hotter filament and a longer life. Here's a highlight. The first is the addition of a small amount of halogen gas, typically iodine or bromine. The second is a fused silica or similar heat-resistant glass that surrounds the filament gas. This allows the tungsten evaporating from the filament to be picked up from the hotter wall and recycled back into the filament. Like standard incandescent lamps, halogen lamps are made in many sizes, shapes, and wattages. When compared to a standard incandescent lamp, they provide greater efficacy, 12 to 36 lumens per watt. Longer life, 2 to 5,000 average hours. The filament of the halogen lamp runs about 3,300 Kelvin, significantly hotter than standard incandescent lamps. Like standard incandescent lamps, halogen lamps have a color rendering index of nearly 100, which is equivalent to sunlight. Lumen maintenance is very good, and the lamp is usually much smaller than the standard incandescent lamp or of similar wattage. Disadvantages: because of higher filament operation temperature, halogen lamps generate a significant amount of ultraviolet radiation. This can damage fabrics, artwork, human skin, and similar surfaces if UV filters are not used. Special handling and cleaning are required because dirt, fingerprints, and similar markings on the surface of the lamp will lead to early failure. There you go. You got to wear those cotton gloves or keep it inside that little sponge rubber casing that it comes in. Don't touch it with your fingertips. Their efficacy is lower than many other lamp types. General use halogen lamps are being phased out or prohibited by law in many countries. And the higher temperature of halogen lamps presents a fire hazard and requires the use of suitable guards or protective luminaire designs. When these are specified by the manufacturer, they're required by NEC section 110.3b, following any rules with the packaging of the item. Fluorescent lamps. Fluorescent lamps consist of a phosphor-coated tubular glass envelope containing a low-pressure mixture of mercury and inert gas, such as argon. Light is produced by passing an electric arc between two tungsten cathodes at opposite ends of the tube. This arc excites the atoms of mercury, causing them to emit ultraviolet radiation. This causes the phosphor coating on the inside of the tube to fluoresce and produce visible light. So the fluorescent tube is actually producing ultraviolet light. When that ultraviolet light strikes the phosphors on the inside of the envelope, those phosphors will emit a visible light. So fluorescent lamps offer good efficacy from 75 to 100 lumens per watt. They also have a long service life, 12,000 to 24,000 hours on average. They'll last you a couple of years, with many lasting even longer. Again, change them out every year. That'll save your ballast. Phosphor coating in fluorescent lamps produces a non-continuous spectrum of light that looks white, but they have a poorer color rendering index than incandescent and halogen lamps. By using different phosphor coatings, the spectral light output of a fluorescent lamp can be made to produce different colors as well as at least 20 different white tones, all with different color rendering indexes. Higher wattages equate to longer tubes. For example, a 40-watt straight tubular lamp is about twice the length of a 20-watt lamp. Fluorescent lamps have two unique electrical requirements to start the lamp. A high voltage surge is needed to establish an arc in the mercury vapor. Once the lamp is started, the gas offers a decreasing amount of resistance, which means that current must be regulated to match this drop. Otherwise, the lamp would draw more and more power and rapidly burn itself out. The ballast provides the required voltage surge at startup and then controls the subsequent flow of current to the lamp. Fluorescent lamps and luminaires are categorized into the following classes. You've got preheat. They preheat the lamp and luminaires, have a delay between when the lamp is turned on and when the light is produced. Rapid start luminaires designed to start the lamp by continuously heating or preheating the lamp electrodes by means of heater windings built into the ballast. To start properly, the luminaire must be properly grounded during operation. Standard rapid start lamps draw about 430 milliamps of current. Rapid start lamps have a bi-pin, that's 2 pins at each end. Instant start. An instant start luminaire is used to start specially designed lamps without the aid of a starter. To strike the arc instantly, the circuit causes a high open circuit voltage, about 3 times the normal lamp operating voltage. This is much higher than is required for a rapid start lamp of the same length. Instant start lamps have a single pin at each end of the lamp. So, other terms commonly used to designate types of fluorescent lamps include slimline lamps. It's a group of instant start lamps with single pin bases. High output lamps, a group of rapid start lamps that produce higher light levels by operating at a higher operating currents, 800 milliamps to 1,000 milliamps. So that's high output lamps. That's a highlight. These lamps have a recessed double contact base and require a matching lamp holder. They call those tombstones. Very high output, group of rapid start lamps that produce even higher light levels by operating at 1,500 milliamps. Because of the higher operating currents involved, the lamps also have a recessed double contact base. Very high output lamps are typically used in factories, warehouses, gymnasiums, and open areas. Then we have the compact fluorescent lamps. This one is a compact fluorescent lamp, but it's shaped to look more like a standard incandescent. It has 2 pins. You push it in and turn it less than a quarter turn, but you have to push it in and then lock it in by turning it. This one has an Edison base, so you can use it in regular lighting fixtures. T5 lamp. T5s are newer and more efficient lamps than T8s or T12s. They can only be used with electronic ballasts and produce nearly twice the light output of traditional T8s or T12s. That T rating is the diameter in eighths of an inch. So a T8 is 8/8. A T8 is 1 inch in diameter. A T12 is 12/8. It's 1.5 inches in diameter. So a T12 is the oldest fluorescent lamp, and it's 1.5 inches in diameter. Then they came out with T8s, and they're 1 inch in diameter. Now they have T5s. They're 5/8 of an inch in diameter. And you need special tombstones. You can't use a T5 lamp in a T8 or T12 fixture. They won't fit. So if you're in Home Depot and you see a T5 and they say how efficient they are, and you go, oh, that's great, I'm going to put those in mine. Not if you have a T8 or a T12 fixture. You need to replace the fixture. The life of a fluorescent lamp is affected by the number of times the lamp is started. Frequent starting of fluorescent lamps results in shorter lamp life. You know what? That's a highlight. While continuous operation provides the longest lamp life. The typical fluorescent lamp rating given by one major manufacturer uh, are based on 3 hours of operation per start. For example, if a lamp is rated as having an average life of 12,000 hours, this is based on the lamp being turned on 4,000 times and left on for an average of 3 hours per start. Okay, very good. The advantages of their lower surface brightness and many other types, leading to less eye strain or difficulty in seeing near objects, more efficient than incandescent or halogen. The disadvantages, there are special disposal requirements due to mercury content. Lamp and ballasts must be compatible, shortened lifespan with frequent starts, and the phosphor coating is inefficient when it's cold or hot with little light output in these environments. So it's got mercury vapor inside of it, and it's got phosphorus coating on the inside of the envelope. These things are a health hazard. Don't play with them. I see these TikTok or YouTube videos where they're playing Darth Vader and they've got the fluorescent tubes and they're smacking them against each other and they're in a shower of glass and phosphorus and mercury vapor. It's like, man, you can't imagine how stupid that is. These guys, they don't know what they're doing. They think it's hilarious. They don't do it. Dispose of them properly. Wear at least a particle mask when you're disposing of them. And don't use them as a lightsaber. Light emitting diodes. It's been known since 1909 that all diodes emit light. However, it took a few decades for diodes to be used in lighting applications. These special diodes are called light emitting diodes. Initially, their light output was only infrared and red. New semiconductor materials have allowed LEDs to produce yellow, green, blue, violet, and ultraviolet colors. Like fluorescent tubes, white LEDs use a phosphor coating on a blue or violet LED to produce white light. Using two phosphors results in a color rendering index of only 60 to 70, but more recent 4-phosphor blends have allowed the production of LEDs with a color rendering index as high as 99%. That's great. That's good. Those are very bright and they're very close to sunlight. All right. Unlike incandescent lamps with a filament and energy losses of greater than 90%, LEDs lose very little energy. Electrons in the diode produce light through a process known as electroluminescence. Because of this, LEDs are far more energy efficient. Okay, that is a highlight. Electrons in the diode produce light through a process known as electroluminescence. All right. Characteristics of LEDs require a very stable DC power supply, just a few volts. This low voltage power supply is called a driver. Drivers can be designed for a single LED or for an array of LEDs connected to in series. All right. They're using them in everything nowadays. Those LEDs, they're very efficient. You can get a lot of colors in the spectrum. A lot of times they're passing light through an LED. That diode will actually be 2 diodes in parallel so that electricity can pass in one direction and then it can pass back in the other direction and give you a different color. That's how you can get green in one way and red, or red and yellow, or you can go quickly between a red and a green and it'll look blue. So you'll get all these different colors of the spectrum when you're using those LEDs. All right. LED luminaires are now used to provide energy efficient, low maintenance lighting in a variety of applications, such as landscape lighting shown here. High output LEDs are now being used for luminaires on streets, roadways, high bay warehouses, and sports stadiums. They're using them. There's a billboard in my neighborhood outside of a jewelry store that uses LEDs. And when I'm going to work, it's dark. The sun's not up yet. And that sign, if it changes the ad and the ad that it's showing has a lot of white background, if it's a big white billboard with a little bit of writing, it's blinding. Like they should make some kind of a law saying you have to tone it down. You can't be over a certain given number of lumens being produced by this sign. Because I'm telling you, I can't see the traffic. I can't see the road in front of me. It's horrible. I have to put my hand up and shade my eyes from it just so I can drive. It's a danger. Let's see here. Advantages of LEDs. Well, they're highly efficient. They're dimmable. They're smaller lamp size. They're lower operating temperature. Repeated starts have no effect on the lifespan. No visible warm up time. No requirements for cool down. They're shock and vibration resistant. They're changeable colors using color changing RGB LEDs. They provide a variety of lighting effects used using special controls. They can be designed for use in a wide temperature range from -40 degrees Celsius to 100 degrees Celsius. The disadvantages: the current and lifespan are dependent on changes in voltage. An uncontrolled spike or surge in the incoming power can burn out a driver or an LED. The greater amount of blue and many white LEDs, roadways, and street luminaires increases the light sky light pollution. Poorly designed drivers impose a very large amount of harmonic noise on a power line. Wow. For studio, broadcast, and film applications, including sporting games, typical LEDs have gaps in their color spectrum. With a low color rendering index of 60 to 80, LEDs with very high color rendering index of 95 to 99 are available for these uses, but at a higher cost. So when you're on the kiss cam at the baseball game, people aren't seeing the real you. Sorry. It's a poor imitation of the real thing. When turned on, LED drivers have a higher inrush current of up to 100 times the steady state operating current. It only lasts for a few milliseconds, but when turning many LEDs on at once, the inrush can trip the circuit breaker. Okay. Retrofitting. Various fixed color LED lamps are available for use in existing luminaires. LED spotlights are also available with different beam spreads and shapes. Very good. So retrofitting is taking an LED and putting it where you used to use an incandescent. And retrofitting used to be difficult. Now you just screw in the lamp and you're done. So it's kind of nice.